In the previous video lecture, I have shown the basic of NMR spectroscopy with the history, the instrumentation, and some structural elucidation by this spectroscopy. Now, in this video, I will discuss the basic in depth. So, let's start. First of all, nuclear spin states. Many atomic nuclei have a property called spin. The nuclei behave as if they were spinning. All atomic nucleus that contain an odd number of proton and neutron have an intrinsic magnetic moment and angular momentum. In other words, a non-zero spin, while all nuclides with even number of both have a total spin of 0. The more common nuclei that possess spin include the most commonly studied nuclei are proton and carbon, although nuclei from isotopes of many other elements have been studied by high-field NMR spectroscopy as well. So this shows the element and nuclear spin quantum number. So and also number of the spin states. So how it is measured? Many atomic nuclei have a property called spin. The nuclei behave as if they are spinning. You can see the atomic number: hydrogen, carbon, nitrogen, oxygen has been shown. The atomic mass has also been shown. Then spin quantum number has also been shown here. Okay, actually our atomic number and atomic mass, if these are odd, okay, then we can have half integer, and if any one of them is odd, then we have the full integer 1 to 3. Okay, like proton or nitrogen is both of them are uh, full integer. Okay, then however, if our atomic number and both atomic mass are both even, okay, for example, for oxygen both of are even, for carbon 12 and 6 are even, so in this case they will have 0. For each nucleus with spin, the number of allowed spin states it may adopt is quantized and can be determined by the nuclear spin number of L. Okay, so L is a physical constant. There is 12 plus 1 allowed spin states. So I've already shown the what should be the spin state. Actually depends on the value of 12 plus 1. Here for L spin quantum number, this is the value of L. Okay, if L is 1, that means 2 plus 1 is equal to 3. If L is 0, okay, so you can easily measure this. For this, for the 0 it will always be 0. Then put the value here. Notice that the nuclei of an, so all that I have discussed has been given here. Just go through this. So hydrogen nuclei can adopt only one or the other of these orientation with respect to the applied field. The spin state plus half is for lower energy since it is aligned with the field, while the spin state minus half is for the higher energy as it is opposed to the applied field. So actually this happens for plus positive and negative spin. If it is negative, that means it would be in higher energy state. Okay. So hydrogen has two states. One spin if it rotates in that location, then spin negative one would rotate on the opposite direction. So this shows the case whenever no field is applied, then all of them are similar. But whenever applied field is administered, then you can see the energy separation, the level separation, plus half and minus half. Yes, plus half is for with field and minus half is for against the field. So you can see the applied field. So B naught, it means the applied magnetic field. So here it has been shown. So plus half is for lower energy and minus half, this is the minus half, this is higher energy, this is lower energy. So absorption of the energy, the nuclear magnetic resonance phenomenon occurs when the nuclei aligned with the applied field are induced to absorb energy and change their spin orientation with respect to the applied field. in practice, this energy difference is function of the strength of the applied magnetic field. Actually, spin orientation happens due to the applied field, and as I have shown in my previous video, that whenever proton is receiving some energy due to resonance, then they aligned in the same direction or in the opposite direction to that of applied field. Okay, because they absorb some energy. So the calculation of the energy has been shown here. Here gamma means gyromagnetic ratio, and frequency, that is the frequency, and B naught means applied field. Okay, so here the energy difference we know is equal to S nu. Planck constant nu is the frequency of the absorbed energy. Then gamma is the gyromagnetic ratio of the nucleus. Okay, then B naught is the strength of the magnetic field. So for some atoms, gyromagnetic ratio has been shown, and two moment we can observe from this theory, that is magnetic moment and angular momentum. So magnetic moment is a vector quantity that describes the strength and orientation of the magnetic field produced by a magnet, and angular momentum is a physical quantity that describes the rotational motion of the object. So angular is related to the rotational, and magnetic is just orientation and strength of the magnetic field. And gyromagnetic ratio is nothing but the magnetic moment, the ratio of the magnetic moment to the angular momentum. So both of their ratio is known as gyromagnetic ratio. When a magnetic field is applied, the nucleus begins to precess about its own axis of spin with angular frequency of mu, which is called Larmor frequency. Actually, upon the addition of magnetic field, okay, this frequency is observed. The frequency at which a proton precesses is directly proportional to the strength of the applied magnetic field. As I've shown in my previous lecture, that yes, actually how much aligned would your student be, it actually depends on the seriousness or the uh, uh, nature of the teacher or the faculty member. If the teacher is very strict, then the student would be very much aligned in the PT. Okay, and if the teacher is not so strict, or are very much friendly with the students, you can see that yes, the students are not so much aligned and they are just moving here and there. So for a proton, if the applied field is 1.41 Tesla, the frequency of the precession would be 60 megahertz. Since the nucleus has stars, the precession generates an oscillating electric field of the same frequency. If radio frequencies of the frequency are supplied to the precessing proton, the energy would be absorbed. That is, when the frequency of the oscillating electric field components of the incoming radiation just matches the frequency of the electric field generated by the precessing nucleus, the two fields can couple and energy can be transformed from the incoming radiation of the nucleus, thus causing a spin change. Actually, yes, here is the resonance. Okay, here is the evidence of resonance. If the the nature of the teacher matches with the students, then students can receive information or get motivation. And actually this happens if the applied magnetic field are in very good association with the nature of the the spinning, okay, oscillating energetic field uh, is aligned with the nature of the nucleus, the precessing nucleus, then resonance will happen. Okay, this condition is called resonance, and the nucleus is said to have resonance with the incoming electromagnetic wave. So atomic nuclei that exhibit the nuclear magnetic resonance. The NMR occurs only in atomic nuclei that possess non-zero nuclear spin quantum number. A nucleus show non-zero nuclear spin quantum number if it has either odd number of proton and odd number of neutron, or both odd. When spin electron nucleus is placed under the magnetic field, it takes several energy orientation based on their spin number. Okay, and it can also be detected by 12 plus 1, where L is the spin number. So I have already shown this in previous slides. So here the resonance, this is the lower energy, this is the higher energy. For the uh, input of the energy, you can see from lower state it come into the higher state and spin has changed. So precessional frequency of a nucleus, I have also shown this equation. This means the gyromagnetic ratio. the ratio of the magnetic and the angular momentum. This is the strength of the magnetic field, and this is the spin frequency. So here are some calculation. Actually, sometime we talk that yes, that was 300 megahertz NMR or 600 megahertz NMR. Actually, this calculation comes from there. Some gamma values for nuclei, some nuclei. The way electrons have spin states or angular momentum and uh, tend to pair together with an electron of the opposite spin to form pairs. Neutron and proton has also spin states and can pair together. This produces pair that overall have zero spin or angular momentum. Actually, the generation of the magnetic angular momentum and the direction magnetic dipole has been shown here. I have discussed it in previous slides. Just go through this. So the chemical shift and shielding. At a given frequency, all proton will absorb energy at the same value of the magnetic field. However, the field experienced by a particular nucleus differs in magnitude from that of applied field because of the shielding effect by the neighboring electron. Okay, so what is actually the shielding effect? Shielding effect is just due to the presence of some protons and the protons electron. These sometimes cause shielding. Okay, but when deshielding occurs when uh, there is availability of some heteroatom or some electronegative atom. So actually shielding is due to the presence of proton, and each proton has one electron, and shielding by electron, nothing else. It is because of varying degree of shielding that protons in different chemical environment absorb at different values of the applied field. Differences between such absorption are referred to as chemical shift. All protons are subjected to diamagnetic shielding by electrons bonding them to another nucleus. Under the influence of the applied field, this electron circulates around the field direction, and in doing so they create some localized magnetic field in opposite to the applied field. Such magnetic field is called diamagnetic anisotropy or diamagnetic shielding. Actually, shielding is happening due to the electrons. The magnitude of the opposite field is directly related to the electron density around the proton, which is in turn determined by the electronegativities of the neighboring nuclei. So in NMR, no attempt is made to measure the exact resonance frequency of any proton. Instead, a reference compound is placed in the solution of the substance to be measured. Okay. The resonance frequency of each proton in the sample is measured relative to the resonance frequency of the protons of the reference substance. In another word, the frequency difference is measured by directly. The standard reference substance that is universal is called tetramethylsilane or TMS. This compound was chosen initially because the protons of the methyl group are more shielded than those of most other known compounds. When another compound is measured, the resonance of its proton are reported in terms of how far they are shifted from those of TMS. So actually, TMS is a standard. In UV or fluorometry, we sometimes provide or use some blank. Okay, actually TMS is the blank of NMR spectrometry. Okay, for sample preparation or sample application, we need to put some blank, and actually these TMS work as the blank. So this is the structure of TMS. How much chemical shift we will have? Actually, there would be no chemical shift because 12 hydrogen and all of them are in same environment as very much hydrogen here. So their position would be 0, and it has been standardized as 0. So highly shielded is the most shielded. Okay. So why is chemical shift expressed in ppm rather than magnetic field strength or frequency? So this is very important question. We have seen in previous lecture also that in chemical shift is measured in ppm, 0 ppm, 2 ppm, to 12 ppm, 13 ppm. Okay, but why it is not in Tesla or frequency? Because our equation was in nu is equal to um, some our equation shows b, our equation shows nu, our equation shows some gyromagnetic ratio. So why these are not? So we'll see this application here. Actually, whenever the ratio of the resonance frequency is shown and we have some value like 5 by 3. For example, it is for standard 60, this is for standard, and 100 maz, it is for some applied field. Okay, so actually we'll have a value like 5 by 3. So 5 by 3, so this value is some much more difficult to interpret. So actually what 5 by 3 means. Okay, hence for a given proton the shift from TMS is larger than the 100 mhz and range than in 60 megahertz. This can be confusing for worker. Yes, this is the main reason. So I put a value like 5 by 3. So what do you mean by 5 by 3? So trying to compare the data if you have a spectrometer that in different strength of applied magnetic field. This confusion is easily overcome if one defines new parameter that is independent of the field strength. For instance, by dividing the shift in hertz of a given proton by the frequency in megahertz of the spectrometer which the shift values are obtained. Okay, so by using the delta we actually measure this. So if it is expressed in that way, then you can easily measure the chemical shift like 2.7. So here is the way we keep our delta value from 0 to 12. So NMR graph, actually I have already shown this. You can easily understand that this one is more shielded, means higher field. This is called up field. This is for electropositive atom. Okay, and it has a very 0 1 2 3 value, and it is less shielded, it is lower field. This is also called down field, and this is for this shows the higher value. Okay, now chemical shift, actually how chemical shift occurs. So in NMR the chemical shift is the resonant frequency of the nucleus relative to the standard. Since the numerator is usually hertz, the denominator is megahertz. Delta is expressed in ppm. Okay, we have already shown this. The detection frequency for proton, carbon, silicon nuclei are usually referenced against TMS, tetramethyl which is assigned the chemical shift of 0. Other standard material are used for setting the chemical shift for other nuclei. So what is chemical shift? Because of the varying degree of shielding that protons in different chemical environment absorbs at different value of applied field, difference between such absorption are referred to as chemical shift. So actually these informations can be found from NMR signal, as we have shown in our previous lectures. Then splitting, position, intensity, and number. So why TMS is reference standard? It has some properties. Okay, it has some characteristics which make it very suitable for keeping this as a reference standard in NMR. For example, an ideal reference standard should be chemically inert and non-reactive, then easily removed from the sample after measurement, and should have a single sharp resonance peak. The peak is display should be far away from the most peaks normally observed, and should not interfere with the resonance normally observed for organic molecule. And all of these properties can be found in TMS. So tetramethylsilane fits all of these characteristics in that it is chemically inert. Due to its high volatility, it can be easily removed from the sample by applying high volume. Since all 12 hydrogen atoms of TMS are equivalent, they would provide one single strong peak. As silicon atom is highly electron donating, it shields the proton of the TMS, pushing the peak every upfield. As a result, most signal of organic compounds are obtained downfield. Thus, the signal of the peak would be separate from the signal normally observed organic molecule. Now, I have already discussed instrumentation. Just go through this. So, the pulsed Fourier transform in instrumentation. The working principle has been discussed in previous lecture. Just go through these contents. Okay, now we'll look into this. So this shows the overall chemical shift and the availability of the peak. So electronegative atom can be found here and electropositive atom can be found in that direction. This is for downfield, downshield. Okay, this is for upfield and upshield, shielded also. And you can also the more electronegative atom you will have, the more it will get deshielded towards 19, 11, 12. Okay, so approximate chemical shift ranges for selected types of proton has been shown here. You can see that for carboxylic acid, okay, aldehyde, amide, you can see the range. For benzene, you can see it is within the 7. Okay, for aromatic compound it is 4 to 5, 6. Okay, then these are for some aliphatic compound. Actually, it is not necessary to memorize this. Just keep the theme in your concept. Okay, the aliphatic, this shows the some unsaturated. Okay, this shows the electronegative atom attached with carbon. Then this is for alkene. This range is for benzene. We see this in 7. This is for aldehyde and this is for acid. So this is the overall thing. Just if you can keep this idea in your mind, then you can easily detect any other compound, and you can also put the uh, spectrum yourself if I give you any structure or any compound. Now we'll discuss different factors that affects the chemical shift in NMR. First of all, electronegative atom. Actually, electronegative atom will deshield the carbon or the hydrogen. Then this will shift this into downfield. This is the thing. The trend of chemical shift that is easiest to explain is that involving electronegative elements substituted on the same carbon to which protons of interest are attached. The chemical shift simply increases as the electronegativity of the attached element increases. Okay. The electronegative substituent attached to the carbon atom because of their electron withdrawing effect reduce the valence electron density around the proton attached to the carbon. Okay, I've already told this. In other words, electronegative substituents on carbon reduce the local diamagnetic shielding in the vicinity of the attached protons since they reduce the electron density around those protons. Substituents that have this type of effect are said to deshield the proton. The greater the electronegativity of the substituent, the more it deshields proton, and hence the greater is the chemical shift of the proton. Multiple substituents have a stronger effect than single substituent. Okay, you can see here chlorine. It will pull the electrons of hydrogen. So hydrogen can no, still be shielded. It is now deshielded. Okay, you can see here the more electronegative, the more deshielding from 0 to higher value. Okay, most deshielded. Okay, the more atom it would have, the more would be deshielded. 3 electronegative atom more deshielded, 1 electronegative less deshielded. Okay, moreover the more would be the nearby one, the more would be deshielded. You can see this would be the least, this should be the second highest, and this should be very deshielded. Then anisotropic effect. Actually, this is for the pi electron, or you can say uh, delocalized benzene ring. There are some type of proton with chemical shift that are not easily explained by the simple consideration of the electronegativity of the attached group. The presence of nearby pi bond or pi system greatly affect the chemical shift. For instance, consider the proton of the benzene and other aromatic system. Aryl protons generally have a chemical shift larger than the expected value. Alkyne, alkenes, aldehydes are also have the proton with resonance value that are not in the line with the expected magnitude of any electron withdrawing or hybridization effect. In each of these cases, the anomalous shift is due to the presence of an unsaturation system in the vicinity of the proton in question. Actually, this anisotropic effect is due to the pi electron because they are not localized; they are delocalized. Okay, like benzene, when it is placed in magnetic field, the pi electron in the aromatic ring system are induced to circulate around the ring. You can see delocalization. The circulation is called a ring current. Okay, this moving electron is in turn generate a magnetic field. I have also shown this. To draw the structure of the benzene, we actually draw in that way. This is the ring. Okay. So in magnetic field covers the magnetic field covers a special volume large enough that it influences the shielding of the benzene hydrogen. The benzene hydrogen are said to be deshielded. Okay, because what? Because of the delocalization by the diamagnetic anisotropy of the ring. In electromagnetic terminology, an isotropic field is one of either uniform density or spherically symmetric distribution. In anisotropic field, it is not isotropic, that is non-uniform. Actually, what is isotropic means? Isotropic means uniform. Okay, and anisotropic means what? It is opposite to uniform. Because of this electron density, the delocalization, it is not isotropic. Isotropic means uniform. That means anisotropic, like hydrous and anhydrous. Hydrous means it is water containing, and anhydrous means it is dry, not water containing. This is the same case. A proton attached to a benzene ring is influenced by three magnetic fields: the strong magnetic field applied by the electromagnetic of the NMR spectrum, and the two weaker field, one due to the usual shielding by the valence electron around the proton, and another due to the anisotropic generated by ring system. So these are the cases actually which called the deshielding. It is the anisotropic effect that gives the benzene proton a chemical shape that is greater than expected, because for alkane it was shifted towards 3 to 4, but for benzene it is shifted towards 7 for this anisotropic effect. These protons just happen to lie in a deshielding region of the anisotropic field. If a proton were placed in the center of the ring rather than on its periphery, it would be found to be shielded, since the field lines there would have the opposite direction from those of periphery. So shielding and deshielding has been shown here. So the ring current in benzene, the delocalization, the deshielding. Okay. Also anisotropic effect in alkane, the deshielding has been shown towards the downfield. In alkyne, you can also see the deshielding. Okay, hydrogen is shielded, but for secondary magnetic anisotropic field has occurred. Then hydrogen bonding, deshielding the proton. You can see, for example, this is a hydrogen. Okay, it is shielded by a proton. Very good. But think that if it forms a hydrogen bond with another hydrogen, like hydrogen bond is formed in that way. Due to this hydrogen bond, it looks like an electronegative atom. Okay, this electronegative atom will also create the same effect as that of nearby atom. Then this oxygen will pull the electron towards where? Towards here. That means it would be deshielded. So due to the hydrogen atom, it would be deshielded. Okay, that means it will take the it will deshielded it and shifted the downfield in the NMR spectrum. So deshielding occurs in carboxylic acid. That is why it is downfield to 10 to 12 ppm. So very far downfield. Okay, now you can also see here in this structure there is also hydrogen bond. So it will be downfield toward where? 14 ppm. You can see way downfield because of the hydrogen bond. Okay, so typical ranges for proton with variable chemical shift. You can see here for variable chemical shift for enol will also have very downfield, because it is containing hydroxyl, also containing some alkane pi system. Okay, then hybridization effect. If I describe this simply, you'll find that for 3 degree, I mean this would be from 0 to 2. The more hydrogen, the more shielding. But if hybridization is looks like C and C 3C, then it would be toward the downfield actually. So this is the thing that is actually happening towards the hybridization. In a simple way, I will say that if it is sp3 hybridized, very good, because methane has sp3 hybridized. It is very close to 1, very good. But whenever it is having some sp2 or sp hybridization, that means it is toward the pi system, and pi system means downfield. Okay, so then it will be down towards 5 to 6, like that. And aromatic C carbon, sp2. Okay, so 7 to 8. Aldehyde, it contains the sp2 hybridization 10. Then carboxylic acid, sp2 hybridization 10 to 12, but sp3 contains 1. Okay. Then spin splitting, I have already discussed this. Now I will discuss the theory of this. So singlet, doublet, triplet, quadruplet, this happens because of the interaction with the neighboring hydrogen and is called spin splitting. In another word, magnetic interaction that occurs between two or more protons, most often through the intervening electrons, thereby result in splitting of the spectral lines is called spin coupling. So here, why spinning occurs? Splitting occurs due to the uh, some effect of the nearby proton. So spin splitting arises because the hydrogen on adjacent carbon atom can sense one another. The hydrogen on carbon A can sense the spin direction of the hydrogen of the carbon B. In some molecule of the solution, the hydrogen on carbon B has spin plus half, and if it is minus half, then obviously one will sense another. Okay, so the reasons have been described here why splitting occurs, and just go through this. So you can see here, for A we'll have a peak, for B we'll have another peak. So for this splitting, actually this arises. So proton A also splits proton B, since proton A can adopt two spin states as well. The final spectrum of the situation consists of two doublets. Actually, two doublet can be found. For 1 plus 1 is equal to 2. That means 2 splitting. Two doublet will be observed in any situation of this type except one in which proton A and B are identical by symmetry. If they are both identical, then we will not have splitting. Okay. Now there some picture has been shown. I think you can easily understand the peak if you go through my previous lectures, because in my previous lecture I have described the nature of the peak and the identification and structural elucidation by understanding different peaks. Okay. So here different peaks has been shown. Now I think you can easily understand the splitting, the pattern of splitting. So NMR spectrum of bromoethane has been shown here. This for TMS. Okay, you can see here a peak in 0. Actually, this is for TMS. Okay. Then bromide, here is one, here is another one. So think that is B, that is A. So A would be here, where A would be here, and B would be here for electronegativity. So their position has been defined. Now for A, so its height would be higher because it contains 3 hydrogen, and its height would be lower because it contains B contains 2 hydrogen. Okay. Then splitting. So how splitting will happen? The splitting will actually depend on the nearby atom. For A, look at the nearby atom. It has 2. 2 plus 1 is equal to 3. That means 3 splitting. You can easily see the 3 peak here, 1 peak here, another peak here, another peak here. And for B, how much splitting will have? 3 plus 1 is equal to 4. 4 splitting. You can see clear peak of 4 peaks. Okay. Then intensities of multiplet peak, Pascal triangle can be applied here. So singlet, doublet, triplet. So how would be the height? Actually, it has been shown. It follows some binomial distribution. So how actually spin splitting happens? Due to the sensing of the nearby carbon. Okay, nearby carbon's hydrogen. Just go through this. I have discussed all of them earlier. You can see 2 neighboring atom and plus 1 is equal to 2 triplet. So for this we will have a triplet. Okay, for this we will have a doublet. So the coupling constant, one of the very important concept regarding the splitting. The distance between the peaks in a simple multiplet is called the coupling constant. Okay. The coupling constant is a measure of how strongly a nucleus is affected by the spin state of its neighbor. The spacing between the multiplet peaks is measured on the same scale as the chemical shift, and the coupling constant is always expressed in Hz. In ethyl iodide, for instance, the coupling constant is 7.5. It means the distance between the splitting peaks. The coupling constant is the distance between the peaks in multiplet. So you can see the difference of the distance is the J. J is the coupling constant. You can see here the peak, the distance 7.5 hertz. Okay, so in 100 megahertz, coupling constant are constant. So they do not change in different field distance. You can see the coupling constant is same. Here 100 megahertz has been provided, then here 200 megahertz magnetic field has been provided, but in all of the cases coupling constant is better, same. Okay, however resolution is better in case of the more strong magnetic field you will provide, the more would be your resolution. You can see here better resolution. Okay, so you can see for 50 megahertz, 100 megahertz, 200 megahertz, the final one 200 megahertz, the peaks are much more identical. That means very resolution is very good. You can separate them as three compounds here. Okay, I mean three peaks here, but you cannot separate them. Okay, so notation for coupling constant, actually vicinal coupling and geminal coupling, these two are present. Actually this shows the intervening bonds between them. Okay, so for geminal we use this, and for vicinal we use this symbol. And another coupling is long range coupling. You can see here another hydrogen, here is a hydrogen. So how much hydrogen between them? 1 2 3 4, 4 bond, so 4J. Okay, so vicinal trans since geminal, so this hydrogen, you can see 3 bond between these two hydrogen, then 3 bond between these two hydrogen, 1 2 3, and 3 bond between these two hydrogen, so 3J. But here is only 2 bond between them, another hydrogen, here is 2 hydrogen, only 2 bonds, so J 2J. Now you can easily understand the doublet, triplet, quadruplet, quintet. Here is the Pascal's triangle. So from the NMR we usually get this information. Okay, SPIN, I have already put the shortcut technique for this. Now we'll discuss different 2D NMR. These are some improved NMR. In 2D it just looks like 2D TLC. In 2D TLC we performed how peak are shown. Actually in 2D TLC we have shown that you have some peaks like that. Okay, then you have just rotate this in 90-degree angle, then how your peak has appeared. Whenever you put this in 90-degree angle, then just put this in 90-degree. Okay, then you run another TLC, then this will appear. All of the compound will be separated again. You have very clear idea about the nature of the compound. Like 2D NMR technique is also available. By 2D NMR technique, it provides information about the chemical shift and coupling constant. 2D NMR allows the correlation of the two different types of interaction. So it provides the correlation. Okay, two independent radio frequency pulses are applied to the sample, resulting in the series of data points that form a matrix or a spectrum. Each data point corresponds to a specific combination of the resonance. So there are different types of 2D NMRs, like correlation spectroscopy or COSY, heteronuclear correlation spectroscopy like HETCOR, then heteronuclear multiple quantum coherence like HMQC, then nuclear Oberhauser effect spectroscopy like NOISY, then incredible nuclear abundance double quantum transfer equipment like inadequate, then total correlation spectroscopy like TOXI. Okay, so this shows the 2D NMR. Okay, from here you have a peak, this is visible, then another peak you will have in that direction. So 2D direction, here is a peak, another peak is here. Okay, so the COSY, TOXI and NOISY, so you can easily analyze this by, and you can also see the correlation among them. Okay, so for clear visualization we usually use this 2D NMR. So application of 2D NMR is it simplifies analysis of more complex or ambiguous cases such as protein, and it obtains structural information not accessible by one-dimensional NMR method. So these are the types. It has been shown again. So different types of 2D NMR. Just go through this. By which NMR we do which analysis. In homonuclear correlated spectroscopy, correlation between the proton that are coupled to each other is determined. Then in TOCSY, uh, it uses spin lock for coherence transfer. In head core, usually between the proton and carbon resonance. In noisy or noisy, protons that are close in speech, the correlation is measured. This is the single most powerful NMR technique for determining the three-dimensional structure of molecule, from conformational of small molecule to the 3D structure of the small protein. So by noisy or noisy, you can easily do this. And noisy, heteronuclear Oberhauser effect, then correlation between the proton and heteronuclei that are close in spaces. Then cozy experiment, so commonly used in the radiochemical assignment, cross peaks appear if spin coupling is present. Then protons that are separated by 2 or 3 bonds are usually detected. So Oberhauser effect has been shown here. Just go through these slides, these are not so much necessary. So the overall comparison between the 1D and 2D NMR has been shown. So as that we have discussed in the full slides, these are the 1D NMR, and actually 2D NMR provides better resolution and also provides information regarding the spin correlation, also provides higher sensitivity. Okay, then cross peaks can be studied. Okay, then the signal interpretation is very detailed for 2D. Okay, then equipment setup is also complex for 2D. Then application would be in analysis of mixture or protein structure in drug discovery. Okay, then examples would be COSY, TOXY, noisy, HS, QC, then HMBC, ROISY, inadequate. Okay, HMQC, and the spectrum would be like that. However, there are some similarities. Just go through the similarities. Actually, these both functions in the similar mechanism. Okay, and the main difference is the uh, additional peak that appeared in the 2D. So there are more other similarities between them. So here are also some similarities. Just go through them. So here the NMR spectrum of different chemicals has been shown. I think you can easily now identify the spectrum, as I have also discussed this in previous lecture. So here I will show you some practice problem. Just practice this yourself for the betterment in your examination. So 112 trichloroethane, the alkene, so propyl chloride, so propionyl chloride. So 2 hydrogen means 2 peak. Okay, one is in 1 and another is in 3 position. So this would be in 3 position, this would be in 1 position. Okay, so the triplet would be like that. Then ester, ethanol, I have already shown this. Propanoic acid, so for carboxylic acids H, it would be where, it would be here, singlet peak. Okay, at 11. Okay, then another 2 environment. So for CH2 it would be coaldet, because we should not keep this into consideration, it's very much an longer distance. So for B we'll consider 3 plus 1 is equal to 4, that means quartet. So it should be quartet. And for A, nearby is 2 plus 1 is equal to 3, triplet. It is triplet. Let's practice this yourself. Another solution, just practice this. So for different environment, actually different peaks will appear. Okay, so you can see another one. So all of them will have same environment. The benzene would be 5, because benzene is having some 5 hydrogen. Then CH2 and CH3. For CH2 we'll have nearby one is CH3, so it would be some quadrat, and CH3 it will be triplet. So for this, I think you can easily determine. Actually, for ortho and para, two environment has created. So you cannot take the full benzene into consideration of single one. So it will also have some splitting. Why splitting? Because of the different heteronegative atom, electronegative atom located within the uh, structure. As it is very close to the bromide, which is very electronegative, so it would be very deshielded. So one peak would be appear in 7 6.9, this is 6.9, and another peak would appear in here. So for benzene we will have two separate peak, and another one is for ch2. This is for ch2, we'll have how much peak? We'll have two peak. Okay, for splitting. So here is another NMR spectrum of acetaldehyde. I'll finish this with a tricky one. uh, you can see here ch3cho. Okay, so you may think that yes, for aldehyde will not have peak as like hydroxyl or carboxylic acid. Actually, for carboxylic acid or any alcohol group, the hydroxyl, the H was attached with the oxygen, but here H is attached with the carbon. That means you should take this hydrogen into consideration. That means your hydrogen will keep effect on splitting. So for this hydrogen, so 3 plus 1 is equal to quadrat. Okay, it would be some quadrat, and for this ch3 it would be some doublet. Okay, so these will also keep rule here. So this is the overall lecture from NMR spectroscopy, and this is the second part. If you have still any confusion, please inform me in the comment section. Actually, this NMR is the hardest topic in our pharmacy curriculum. So I have tried my best to keep the lecture as simple as possible. Still, if you have any question or query, please inform me in the comment section. Thank you.